Topic 8.1, Energy Degradation and Power Generation. So in this topic we're going to look at how energy is produced by people throughout the world and sort of the efficiency of that energy. How much do we actually get for that energy that we produce? Now, to really understand this, we need to examine the first law of thermodynamics, and we've actually already looked at this because the first law states that in a closed system energy is conserved, or more simply, energy cannot be created or destroyed. Energy can only be transferred from one form to another. The second law of thermodynamics states that in a system, a process that occurs will tend to increase the total entropy of the universe. But what is entropy? Entropy is very simply the state of chaos or disorder in a system. This cartoon is a good example of the idea of entropy, where you can see the room has become more disordered or more chaotic, and that's the natural state of things. That is to say, things do not build themselves up or put themselves in order. In fact, they do the opposite. They tend to become more disordered. A good example of this is putting drops of dye in water, where you can see that initially the dye is very ordered, very concentrated in one location, but as time spreads out, as time goes on, it tends to spread out and become more disordered. This law is often known as nature's heat tax, and the reason for that is because heat is the most disordered form of energy. It spreads out most easily, and once we turn something into heat, it never comes back. As you can see from this diagram, the energy goes from the more ordered system, where the hot and the cold are separated, to a more disordered system, where energy is transferred from the hot reservoir to the cold reservoir. We can sort of summarize this by saying that it is impossible to convert heat completely into work through a cyclical process, but we could do it in a single stage process. And this diagram is given to you in your textbook, in the Heinemann textbook, where we can see a balloon which is given some energy, some heat is pumped into the balloon. As the balloon receives its energy, it begins to rise. You can see that the balloon is tied to a spindle, and as this balloon rises, the spindle turns, and the energy of the rising balloon is turned into electrical energy. Now, unfortunately, as the balloon reaches the top of its motion, then we can no longer turn the spindle anymore. So now how can we get this thing to repeat itself? Well, in order for it to repeat, what would have to happen is we would have to release some of the energy. That energy would go to a cold reservoir, the cold reservoir being the surrounding air, and then the balloon would begin to descend, and we could coil the spindle back up and have this thing set up to do it all over again. But we cannot get the work converted in a single process. We have to release some of the heat to the surrounding world, and as a result of that, we can get the balloon to descend and we can return the cycle all over again. So as we saw in the past example, it is impossible to extract energy by heat from a high temperature energy source and then convert all of the energy into work. At least some of that energy is going to have to be passed on to a low energy temperature sink. And so diagrammatically, the way we would see this is the energy from the hot reservoir passes to the cold reservoir, and in doing so, we do get some energy from that in the form of work. Therefore, we can see that it is impossible to create an engine using heat that is 100% efficient. It's physically impossible. So let's take a look at an example of this idea of having a cyclical form of energy by looking at essentially the car engine. So if we examine the engine on the left-hand side, you'll see that as the piston slides downward, it pulls in air and fuel. Then, as we spin around through the cycle, the piston is now beginning to move upward. Both of the intake and exhaust valves close, and the air and the fuel become compressed. At the top of the piston's motion, a spark is ignited. It causes essentially a small explosion in which we produce a tremendous amount of heat, and the heat pushes the piston down, and this is where we receive all of our power. Now, after the power portion of the stroke, then the piston continues to rotate around and begin to move upward. At this point, the exhaust valve opens, and we push what's left of the hot air out, and this is where we lose some of our heat energy. That heat energy was not completely turned into power. Some of the heat was still left, and it was pushed out through the exhaust valve to a cold reservoir, the cold reservoir being the outside air. Now, on the other hand, if we don't want to get work, if we simply want to get heat from the energy source, then that can be much more efficient. So for example, in 2008, I replaced our old heater in our house, which was probably no more than about 50% efficient, with a new, much more modern furnace, and this furnace is more than 95% efficient. So why are we able to achieve such a high degree of efficiency with the furnace? Because the furnace does no work. The only work done in the furnace is the fan, which blows the hot air up into the house. Otherwise, the rest of the energy form is heat. Heat is the point of the furnace, and so therefore a furnace can be much more efficient than any type of heat source that tries to be turned into work. Anytime we try to turn heat into work, we end up actually losing most of the energy in the form of heat, and only a small portion gets turned into work. Now this process whereby energy spreads out is called the degradation of energy, and as you can see, it's a process that's a natural part of the process of entropy, the spreading out of energy. And that prevents us from turning all of the energy into useful work. In fact, heat is considered to be the most degraded form of energy because it spreads out so easily. And eventually, all energy will ultimately turn into heat, not only in the small scale, in a small system, but in the larger scale, the universe ultimately will eventually come to a point where the entire universe is at one temperature, and at that point we will no longer be able to do any work. So let's take a look at some examples of energy degradation and the idea of losing energy through the form of heat. Now, one example is the light bulb, which converts electrical energy into light, obviously most importantly, but also into heat. Now, it turns out the regular incandescent bulbs are actually not very efficient because, as you can see, only 10 joules of the 100 joules produced in a typical light bulb turns into light. The other 90% becomes heat. Recently, we've created more efficient light bulbs called the CFLs, or compact fluorescent, in which of 100 joules of energy, we would be able to convert 75 joules into light, and only 25% is converted into heat. And of course, the purpose of a light bulb is to produce light, not to produce heat. The electric motor is another example where electrical energy is converted, but this time into mechanical energy called work, and then of course also heat, as in all cases. So the electric motor is quite simple. The electricity turns a spinning wheel, and then that wheel goes on to do all of the work, whether it's turning a blade on a fan, or whether it's moving a mechanical arm, lifting an arm, or whether it's turning some sort of pulley, which is lifting something. All of that energy is turned into mechanical work, except for the small amount of heat that's also produced. Now, batteries represent a different type of energy conversion, where we convert chemical energy into electrical energy and, of course, the associated heat. I'm sure that some of you might have noticed that when we were using the batteries in our electrical experiments, that the batteries started to get a little bit warm, and that's a result of the fact that, again, not 100% of the chemical energy can be converted into electrical energy. Some of it ends up getting lost as heat. When you recharge your rechargeable batteries or your cell phone, you might notice that they also get warm, and that's a result of the fact that any type of energy conversion is going to produce some excess heat which cannot be recovered. And for our last example, let's look at the car engine, which also converts chemical energy, but this time into work and heat, of course. Now, it turns out that all of the energy produced by the car originates in the form of heat. Of that heat, 80% of it will remain in the form of heat, and 20% of it will be converted into mechanical work, which propels the car forward. So you can see cars are not terribly efficient. Only about 20% of the energy ends up in a useful form. Now, one of our objectives in this section is to understand something called a Sankey diagram. And a Sankey diagram is a visual flow diagram to show where energy has entered into a system or where it has exited from a system. And where it has exited a system, in particular, you have to be able to explain where the energy has been degraded. Now, I already showed you some Sankey diagrams when we looked at the light bulbs, and the energy which is being degraded is that arrow pointing down that says heat energy. In this diagram, one of the advantages of the new light bulbs is that less energy is degraded. Only 25 joules of the 100 that was produced ended up being degraded. In other words, the arrow pointing to the right in these diagrams is the good energy, and the ones pointing down is the bad. So here's energy produced in a power plant, much of which is lost to heat in the environment, used in the power station, lost in transmission. The important part is the part delivered to the customers. That's the good part. Here's energy in a nuclear power plant, and we can see energy is lost in concentrating the fuel rods, in bringing that uranium together. Some of it is left in the fuel rods, some of it goes out as waste heat in the nuclear power plant, and a small portion of it ends up going on to the final customers. Let's take a closer look at our example of the automobile engine through this Sankey diagram. We can see the car produces 72 kilowatts of power, and remember, all of that power is produced from the form of heat. Of that, 57.8 kilowatts is exited from the system, degraded in the form of thermal energy. 14 kilowatts continues on. Approximately 2 kilowatts is lost to the lights, the fans, and the alternator. The alternator is restoring some of the energy in the battery, leaving 12 to go on. Of that 12, approximately 3 kilowatts goes into the transmission, and the remaining 9 goes on to counteract the friction that's internal in the car and the friction from the air. And these last two, that last arrow on the far right, those are the arrows that are allowing the car to propel itself forward at a constant speed. A Sankey diagram doesn't have to simply be a small scale system like a car or like a power plant. It could actually be an entire country. So here's the Sankey diagram for Ireland in the year 2005. Notice on the left hand side we have lots of inputs this time, specifying where they come from, like oil, coal, uranium, wind, hydro, and other sources. And on the right side we have where the energy was going, like agriculture, service, this is like stores, industry like factories, residential, transport, this would be like public transportation, and then also the utility companies are taking some of that energy. Now, of course, they are the ones producing the energy. So you notice that the utility companies actually took quite a bit of the energy that they were the ones actually producing. Not only can Sankey diagrams be for an entire nation, they could be for the entire Earth. So in this case, we're looking at the Earth's energy budget in the form of a Sankey diagram. We see incoming solar radiation, some of which is directly reflected by the atmosphere, the clouds, or the surface. That accounts for about 30%. A small portion is absorbed by the atmosphere, the clouds, or by the land, and then that energy is re-radiated in the form of latent heat of vaporization, water being vaporized. Some of it is absorbed by the clouds and by the air. Some of it is directly re-radiated back into space, and in the end, all the energy that comes in equals the amount of energy going out, and if that were not the case, the Earth would either be getting hotter or be getting colder. And so in this particular Sankey diagram, just as with all the others, the total energy coming in has to be accounted for the energy going out. The last topic to understand is electrical generation. This is really important because electricity is one of the forms of energy that we can transport over long distances. If we think of it in reverse, you'll remember that passing electric current through a wire in a magnetic field caused a force on the wire. And we can use the right-hand rule if we think of conventional current, or we can use the left-hand rule if we think of the electron flow. If we go in reverse of that, rather than putting the current into the wire and having the force put in there, we put a force on the wire and make the wire move, then that will cause an electric current to flow. Now the way that it actually works in a practical sense is that we take a coil of wires and we spin that coil of wires. As we spin the coil of wires, it causes an electric current to flow as long as those wires are in the presence of a magnetic field. Now on a much bigger scale, the way that the electrical generation occurs is with enormous wires, enormous coils of wires. And so in this case, we have the coils of wires from a turbine connected to a turbine. The turbine spins the coil of wires in a magnetic field, and as a result of that, then electric current flows through those wires and is sent out to your house. In the next few chapters, we're going to apply what we've learned about energy degradation and about the visual flow diagrams called Sankey diagrams to understand how energy is produced for human use, particularly in our country where we use about 25% of the world's energy resources, but we only have about 5% of the world's population.